So we are looking at future climate change. So we started by defining climate sensitivity. So we defined then the idea of delayed warming and committed warming. And the big part was to see how the representative concentration pathways, or RCPs, are defined. And it's very complicated. So you need to just get a general sense of it so that you are familiar with all the buzzwords that appear in typical climate reports, and then you have to find a way to translate them into the course. We will get into more and more details of how things are done in terms of projecting and then explaining the projections in terms of probabilities. So one of the things we defined last time was the reasons for concerns, which had unique and threatened ecosystems, corals, Arctic ecosystems, etc. Extreme weather events, which includes heavy rainfall like we are having in India in 2018 summer monsoon, as well as droughts. There are droughts that can become very extreme. Distribution of impacts is basically looking at the uneven impacts of climate events on groups, regions, etc. Then global aggregates are those that combine together from regional impacts and affect global supply chains, global economy, and so on. And there are large singular events which we will talk about in terms of, let's say, the loss of sea ice in the Arctic or ice sheet over Greenland. Each time the level of confidence is important and the time scale over which it will happen is important. For example, the loss of the Greenland ice sheet would occur on a time scale of a millennium or more, for example, and it could contribute up to 7 meters of sea level. We can estimate that based on how much fresh water is locked in, and then you have to account for the adjustments of various continents and the ocean basin because of increased load of the water and so on. And we have some guidance from the paleoclimate where the Greenland ice sheet had disappeared, for example, or before it grew to the present state. The other more formal thing we need to do is define what we mean by likely, unlikely, very likely, as likely as not, and so on and so forth. So we can use the example of temperature for doing that. So I showed the temperature, not the exact same figure, I only showed for 2.5 and 8, but here you can see that all RCPs are shown, and these numbers change a little because remember, it's an iteration process. You define emission pathways, you have technologies, population, adaptation, mitigation options, and the goal you have for what the radiative forcing should be in 2100. So those were defined as 2.5, 4, 6, and 8.5. But once you put that back into the model, sometimes the models do not exactly produce 2.5. They might produce 2.6 because of various feedbacks that are not exactly the same, going from the integrated assessment models to the climate model and back and forth. So you have an iteration process. It's not very important, but because the numbers remain fairly close. So in these figures, these stippled areas are where the confidence is very high because more than 90% of the models agree that the changes are more than 2 standard deviations of the natural variability you have observed by various means over various periods. Okay, so when it is hatched like this, that means the confidence is not as high, or it means that the projected variability is within 1 standard deviation of the natural variability, which means you cannot say that is a change with great confidence. You assume that it's essentially within natural variability. And if you remember the trends we looked at for 1901 to 2010 or so, this region had cooled in some estimates and had remained less warm than other regions in other estimates. So this region, again our favorite Greenland, Iceland, Norwegian Sea region, remains kind of a special place in all the projections, as you can see here. They are not stippled in any of the RCPs, even out to 2081 to 2100. So exactly what the meridional overturning circulation will do, exactly what the Greenland ice sheet will do, and how that will affect the deep water formation, the heat transport, the global thermohaline circulation, and so on, remains within natural variability in that particular spot. But everywhere else you can see there are these little dots, which means stipples, which means that all the models agree that these are going to be substantial changes, more than 2 standard deviations of the present. Whereas when you look at rainfall, we looked at just these two before. Now we are looking at all RCPs, just for illustrating this point again. Here the stippled points are far fewer than the temperature projections, and there are lots of these hatched regions. So the regions where the projected change is within 1 standard deviation of the natural variability is quite large in all RCPs out to 2100 in the precipitation projections. This just re-emphasizes our point that the precipitation observations and modeling and projections and even predictions at weather and climate scales remains an issue. So that should be kept in mind, and we need to communicate such differences in different quantities in a proper way. What is a proper way? It turns out that you cannot just use scientific lingo. These are the number of models that have been used to make the projections. You cannot just explain these how we would communicate in a scientific community in terms of uncertainties or biases. So there is a lot of negotiation that goes on these IPCC processes, where each finding is grounded in an evaluation of underlying evidence and agreement of different evidences, how well they agree with each other and how they differ from place to place or different kinds of evidences, and so on and so forth. In many cases, a synthesis of evidence and agreement supports an assignment of confidence. When you say projection of precipitation or temperature into the future, what is the level of confidence in this projection? So the summary terms are basically divided into limited, medium, and robust. And for agreement, evidences are categorized as limited, medium, and robust. For agreement, they are referred to as low, medium, and high. So when level of confidence is expressed, there are 5 qualifiers that are used: very low, low, medium, high, and very high. And these are expressed with italic fonts, or they are expressed in italics. So virtually certain means the confidence is 99 to 100%. That's very high, also referred to as virtually certain. So you can say the fingerprint of human activities on observed warming is virtually certain. We are almost 100% sure that human beings have contributed to the warming we are observing now. Very likely is 90 to 100%, so just below that. Likely is still way above 50%, so 66 to 100%. About as likely as not means you are hovering around 50%, below or above. So it's possible that it could go this way or that way. Unlikely means it's much below 50%, and very unlikely is very low. Exceptionally unlikely is where we know that it pretty much is not going to happen unless there is something like what is called a black swan event, where something unexpected ends up happening. Okay. There are also additional terms, so extremely likely, more likely than not, more unlikely, extremely unlikely, and so on. So these are essentially negotiated by all governments that sit at the table, and they make sure that the reports are not incomprehensible or biased one way or the other, that the terms mean the same across the globe for all regions and for all quantities that are being discussed. This is important when agreements are made for how each country or region will participate and how they will contribute to reducing carbon emissions, and so on and so forth. So to look at the table then, this is a simplified table from IPCC. Various quantities are shown here: warmer days and nights, more hot days and nights, more warm spells and heat waves, more heavy rainfall, more drought, more intense tropical cyclones, and so on. And the phenomena and direction of trend are listed here. And I just wanted to show this as an example that typically when we discuss temperatures, we end up having high confidence again. So, and assessment of human contribution to observed changes again is very high. And likelihood of further changes, these are observed changes from 1950 onwards. Early 20th century, likely. And as we go out further into the future, the likelihood of further changes is pretty much certain, virtually certain. And the other point is that as you come to rainfall related events, the confidence goes down, as we know already, we repeated several times. It becomes likely rather than very likely, and some of the contributions from human activities become less sure, like more likely than not, and so on. So even into the future they become likely. And there are other details, like if you look at the projections as a time series as we did and we will see again, all of the RCPs tend to remain close to each other out to about 2030, and then they begin to diverge greatly as you go towards 2050, 60 and 2100. That has some implications that all emission scenarios are going to produce similar warming in the next 15, 20 years, which means there may be an opportunity to take great action and change the trajectory of where the future changes will go. So these are all the kind of human dimension of how science is depicted once the scientific calculations are made. Okay? We have kind of already used terms like risks. I think everybody has an intuitive sense. It is the elevated vulnerability to natural disasters in a simplistic sense. So the future climate related risks, vulnerabilities and impacts are estimated through experiments, analogies and models. So experiments are basically where you take the model and you say population will not grow, only emissions will grow, or vice versa, or we will grow more forests and so on. So some factors affect a subject of interest changed while other factors are held constant, so that you can extract the impact of one thing. Like if Amazon forest is completely removed, what happens? If all of Greenland ice melts, what happens? So those are kind of the experiments. When you cannot do such experiments, for example, population experiments may be considered unethical. In that case, you try to use analogies from the past or from different regions. So there are spatial and temporal analogies that are used. So we sometimes paleoecological data to see how something like a meteorite strike changed vegetation, or a large volcanic eruption or a little ice age changed vegetation and climate and so on. And models are basically the models we have been talking about, used for projection, where we said they have all the components of ocean, land, atmosphere, cryosphere, biosphere, and so on. So the impacts are modeled, among other things, mainly for water resources, biodiversity, ecosystem services. This term we have not defined, but a module will be provided where I think you have some sense. Ecosystem services means ecosystems or plants and forests and so on provide food, fiber, medicines, firewood and other things which have a value. When we put value on them, we call them, they are the ecosystem services. Just the shade, for example, during a hot day, that's also an ecosystem service. There are lots of ways to do it. Lots of different estimates are provided for a piece of forest, for example, and so on and so forth. Okay. The other thing I will put out right now is that we will look at the different sectors, like we looked at the reasons for concerns, for example, and we will look at different sectors and different regions. Like when we showed the impacts, we said the Arctic, the North America, South America, Europe, Africa, Asia, Australia, and so on. Those are the different regions. So there are certain risks that are common to all of them, and that includes risk of severe ill health and disrupted livelihoods from storm surges when cyclones come, typhoons come, hurricanes come, and so on, sea level rise, coastal flooding, inland flooding, periods of extreme heat, and so on. So we are having large amounts of inland flooding right now over many parts of India, for example, in 2018. There are systemic risks of extreme weather events. So bridges break down like it happened in Italy recently. Networks, infrastructures break down. Critical services like healthcare or energy supply or food supply may break down. This is common to all. When Hurricane Harvey hit a place like Houston, even though US is a rich country, all these breakdowns happened, for example. Risk of food and water insecurity and loss of rural livelihoods and income, particularly for poorer populations. So there are rural areas even in rich countries, and there are poorer populations even in rich countries. So it is poorer, not poor. So it is just a relative term. There are rich people, there are poorer people, richer people, poorer people. So risk of food and water insecurity and livelihoods in rural areas occurs in all regions and sectors, and risk of loss of ecosystem, biodiversity, ecosystem goods, functions, and services also occurs in all these regions. Keeping that in mind, let's go back to look at our reasons for concerns: unique and threatened ecosystems, extreme weather events, distribution of impacts, global aggregate impacts, and large-scale singular events. The scale shown here is that when it's in the white range, it is basically undetectable change in risk, and then it begins to get moderate, high, and very high. So given the temperature change projected relative to 1986 to 2005, what are the changes we expect in each of these reasons for concerns? So unique and threatened ecosystems, you can see that as the warming increases, it begins to push into the very high risk range. Arctic sea ice and corals are very good examples. It looks like corals like the Great Barrier Reef are already having severe issues, and it needs to be watched in the coming 5 to 10 years whether these changes are irreversible or if the system is able to recover. Extreme weather events are already increasing, as we will see in the context of monsoons when we talk about the Indian monsoon. Distribution of impact, so the unevenness of the manifestation of climate impacts on different groups, richer versus poorer, Asian, or the so-called global south. There is a term called global south, which basically includes all developing countries, developing economies, emerging economies. Of course, there is a corresponding term called global north, which includes all developed countries. Australia is in the south, but it essentially is also under global north, whereas the poorer Asian countries, African countries, South American countries are in the so-called global south. So they face high levels of distribution of impacts for sure. Global aggregate impacts, the current level of this is from 2003 to 2012. The impact is not too obvious, but even the aggregation of impacts into the coming decades out to 2100 is not as severe as distribution of impacts, for example. Okay. Large scale singular event, again, not so sure that they have occurred yet, and the risk certainly can be expected to increase with warming. Those are the kinds of things to remember. So if we go then from the RCP 2.6 to RCP 8.5, the best thing to remember is that this is something that requires that we reduce our emissions progressively as we go into the future decades. By 2100, our emission have to be in fact below where we are right now, which means some technology that we will talk about later has to be maybe invented in addition to reducing emissions, changing energy sources and so on. But the main thing to remember is this is a attempt to keep the total warming to below 2 degrees centigrade with respect to the industrial revolution. So where we started, we need to keep the total global warming to below 2 degrees centigrade. That is the main goal of this lower end of the emission scenario, or CP 2.6, whereas this is called often baseline scenario because it basically corresponds to emissions where we are not doing too many things to reduce our emissions. So we are going to end up in the very high range of concentrations in the atmosphere and total carbon equivalent in the system. So that is something to keep in mind. So the rate of climate change in degrees per year, the risks for terrestrial and freshwater species impacted by the rate of warming, obviously as you go from 2.6 to 4.5, 6 and 8.5. The global average increases, so most trees and herbs cannot keep up as the rate of warming in terms of degrees per year begins to increase. You should get used to that. Degree per year might look small, as I said, but if you take all the ocean, for example, and warm the water by 0.02 degrees and see how much heat that is, you can see how much power that corresponds to and how that number compares with the total electricity production in the world in a year. So those are massive numbers. So that amounts to about 0.2 degrees per 10 years, which is not small. Most rodents and primates cannot keep up as you begin to reach these stages, and you have to remember that many of these rodents and primates, many species have been around for tens of millions of years, and some even more than 100, 200 million years. So they begin to have trouble keeping up with the warming. And as we begin to reach the top estimates of our emission and warming, reaching almost 1 degree per year, which is very rapid rate of warming, most carnivores and split-hoofed mammals cannot keep up. So here it is taken as global average and flat landscapes. The flat landscapes are separated basically because there is something called climate velocity, how fast the climate impact begins to expand its zone, and that is very high for flat lands compared to mountains, for example, or for the oceans. So that is looked at separately, and as you can imagine, if the climate velocity is high, then the risk also begins to increase much more than the global average for flatlands. These are for atmospheric CO2. So if you consider risks for marine species due to ocean acidification and by warming events. So now we have things like heat waves in the ocean. We only talk about heat waves in the land, but now we have examples of massive heat waves in the ocean in the North Pacific, which had huge impacts on fish and mammals. And in the Indian Ocean, we are beginning to have heat waves, and basically pretty much everywhere we are going to now have ocean heat waves in the coming decades if they are not already happening. So ocean acidification only means increasing CO2 and carbonic acid using up of the carbonate ion, you remember. So that makes calcium carbonate formation very difficult. So that is going to increase as atmospheric concentrations increase. If you add warming to it, then you increase the vulnerable taxa affected by warming, like reefs are going to get severely damaged, and they are already showing signs of bleaching and fatigue and so on. The coral echinoderms, mollusks, if you don't know these terms, you should look them up. Foraminifera and pteropods. So foraminifera, we saw that we use them for reconstructing past temperatures. They have calcium carbonate shells, so they are sequestered in the sediment. The calcium carbonate has signatures of temperature or delta O18 in them. So they begin to suffer basically because with acidification, forming calcium carbonate shell is going to be very difficult. So the pH is obviously going to drop. It's as low as 7.8 here. It should be around 8.2 in the pre-industrial, and we're already down to 8.1 or so in the recent decades. So severe problems there. The risk of coastal human and natural systems being impacted by sea level rise, again, coastal risks increase. Adaptation to reduce risks will be needed. We haven't exactly defined adaptation other than saying that it is ways of adjusting to the changes that are inevitable. It could be building seawalls or re-establishing mangroves and so on, but we will come back to more details later on. Okay? Coastal protection and ecosystem adaptation reach their limits at many locations. So, for example, if mangroves are the current natural defenses against sea level rise and storm surges, then with the warming, acidification, human impacts, nutrient pollution, and so on, if the mangroves cannot survive anymore, then you will need new ways of building natural defenses. So, sea level rise is going to be a very severe constraint. So, as you can see, there are many uncertainties whether the high CO2 risks are going to exceed anything we know, and here are our RCPs. This is out to 2300. So, RCPs typically worry about only what happens to 2100, but CO2 remains in the system for many centuries. So, there are some models that ran out to 2300, and large uncertainties remain as you go beyond the current century into future centuries. So, looks like lots of details, and they are, but the main point you want to emphasize is that climate change is going to affect pretty much everything you see on the planet, including our own lives and our health and our movements and the ecosystems and waterways and water quality and air quality that we depend on. So, it's important to just go through and see how future projections are translated into language or scenarios or storylines or narratives and so on to convey our risks for the future. Putting it in another way, risks from climate change depend on cumulative CO2 emissions. So, every year you can measure the CO2 concentration, but there is an accumulation because CO2 has such a long residence time, and that cumulative CO2 emission obviously depends on the annual greenhouse gas emissions over the next decade. So, the baseline is the high emission scenario where we don't do much to reduce. So, we don't do any mitigation or adaptation, and these are the ranges of CO2s, and these are the ranges of, remember we had the CO2 induced warming here and total warming in this range over here, and these are the same emissions giving us a relative term in terms of whether we are going to remain below the 2010 levels or going to go beyond in terms of emission reduction. So, in other words, to get these ranges in 2100 with respect to 2010, we have to basically do emission reduction, which means that there will be a spike. We are at 400. You will spike, and then you have to somehow come down by either taking out carbon from the air, as we will see, it's called CCS or carbon dioxide capture and removal, or renewable energies become so dominant that they will just begin to flatten out the emissions and so on. And those are the risks again shown with respect to the accumulated and yearly emissions of greenhouse gases. Just different ways of depicting these things. So, this is showing the same for scenarios and uncertainties, now with decades shown here and temperatures shown here. So, where we are likely to hit these ranges of temperatures, and these are now the same systems we looked at, the regions for concerns, unique threatened ecosystems, threatened systems, extreme events, global distribution and balance of impacts, This now includes economic, so these are now done by sectors, right? Total economic and ecological impact, risk of irreversible, large scale and abrupt, or what we called singular events. So slight difference in the way it is depicted here compared to 1990s. The risks already is beginning to show in some in the first unique and threatened systems. The risk is going to increase from some to many in this kind of categorization. The increase is going to be quite large for severity of extreme events. There is already sufficient statistics to show this. This is something that you have to kind of educate yourself, because how do you define extreme events? We said 95th percentile and so on and so forth. But how many years of 95th percentile do you observe before you say extreme events are increasing? So it's tricky. Do you want to wait forever, or do you want to take the evidence that is already available and see the trend and say this is not a good trend? For example, in the monsoon, the number of floods since 2012, 2014, 15, 16, 17, now we are in 18. It's been increasing, and the extent of the floods is increasing. It has increased by threefold, as we will see. So I don't think we should wait for too long, but how do you make decisions on that? So it looks like compared to 1990s, the risk has already increased and it's only going to continue to increase. Global distribution and balance of impacts is negative for some regions. So this is where we have to remember that global warming may well produce some winners and some losers, but it depends on lots of the details on how the globally collected population systems, immigration systems, transportations and economies interact with each other. Nonetheless, the models say that the impact is going to be negative for most of the regions over the world. And this has, as I said before, the impact of the vulnerabilities of your neighbors affecting you. So it may not be your vulnerability, but your neighbors are going to begin to impact your vulnerability. Ecological and economic impacts are positive or negative in terms of market impacts, but already majority of the people are adversely affected. There are many measures by which this is done, but if you look at the recessions and how they propagate through the system, how wages don't grow and how they propagate through the system, and how wars spread, how conflicts begin to spread and become interlinked and so on. There is a market impact on economy, there is an ecological impact, and then there is a net impact on humanity. So net negative impacts in all the matrices that are defined are expected to become negative as we go into the next few decades and the warming gets. So some regions will be much more vulnerable than others for sure. So the risk of irreversible, large scale and abrupt transitions right now, as we said, the disappearance of the Arctic ice is one of them, and the Greenland ice melting is one of them. Amazon disappearing is another one. So that uncertainty here remains fairly large, but it is something to watch out for. Okay, so let me use a kind of a heuristic argument from the Potsdam Climate Institute on where the tipping elements or Achilles heel of the Earth system are. Looks kind of crowded, but I think you have already gotten a handle on most of them. So Arctic sea ice, they say it's already tipped, that it's going to disappear. Greenland ice sheet, we talked a lot about. Permafrost, we talked about. Boreal forests, we haven't talked about, but as the warming increases, this is going to become it will probably disappear. And the Atlantic thermohaline circulation, we have discussed again and again. Jet stream, we mentioned, and there is some evidence that with the Arctic ice disappearing, the jet stream will begin to wobble more, and that definitely affects the weather and climate over northern latitudes, over Greenland, Americas, North America, Canada, and Europe and Siberia and so on. And methane clathrates, we didn't explicitly say this, but when we talk about the Paleocene, Eocene thermal maximum PETM that was seen in the long-term climate record we have seen, we said that was a very rapid warming of several degrees, but very rapid, it was over a million or longer, whereas now the warming rate is much higher. And one of the theories of how that rapid warming happened in the past was to argue that the methane clathrates, what are clathrates or hydrates? Essentially the organic matter that is produced in the ocean by photosynthesis or comes through the rivers, organic matter from the forests and so on, gets buried, and then it's not respired immediately because more and more keeps falling on top. It is under cold temperatures and high pressure, so it begins to freeze into bubbles. And if the coastal systems are perturbed either by warming or by human activities, then there is a potential that they will get released, and that is a huge amount of methane. Methane is about 25% more powerful as a greenhouse gas compared to carbon dioxide, but the probability of this right now seems to be low. So mega droughts over Southwest America, already California has experienced repeated droughts in the last 20 years. There is a relation. When El Nino happens, there is rain here, but if this remains cold, as we saw it happen during the so-called global warming pause, then that can become a so-called mega drought. The question is, if you look at the past civilizations that disappeared because of the mega droughts, are we now so advanced that we can live through a mega drought, or will it also create some kind of perturbation? Are there technological solutions like desalinating water to survive the mega droughts? A lot of the companies, especially Silicon Valley, which is there with all the big companies like Apple, Google, Facebook, and so on, already planning to use desalinated water, renewable energy, and so on. So maybe they will find a way to survive. We have no idea how El Nino Southern Oscillation will respond to global warming, but it could go into a permanent El Nino state or a permanent La Nina state. If so, what will be the consequences? So right now there is some evidence that global warming increases the El Ninos and related heat waves, fires and droughts. Amazon rainforest remains a concern. Oceans, we don't know what will happen to oceans' ability to take up carbon through the biological pump. Antarctic ice sheet obviously remains vulnerable entity. African monsoon, Indian monsoon, we don't know what Sahara and Sahel will do. Coral reefs, we said, are already unique threatened systems which are at high risk, and so on. So I wanted to put this so that everything you have learned now, you can begin to stare and say, what is the potential change in these quantities, in these processes? Are they going to become a victim to global warming? Arctic sea ice and the corals seem to be already headed that way. So what are the tipping points that remain in the system? Okay, this is another way to show. This is from Will Stephen's paper, which shows with the range of warming, what are the tipping elements at risk and how are the feedbacks possible. So with 1 to 3 degrees centigrade, Greenland seems to become a tipping point, which would affect the thermohaline circulation for sure because of the impact on deep water formation. Boreal forests will become victims at 3 to 5 degrees. Arctic sea ice and winter ice will completely disappear if we go beyond 5 degrees centigrade, and permafrost will most definitely thaw completely if we warm that much, and that has huge potential to release methane and carbon dioxide. Greenland ice sheet will also affect the Arctic, which will then affect the jet stream, which is already happening, and Amazon forest will affect also the thermohaline circulation because it has a moisture feedback and how much evaporation can happen and so on. West Antarctic and East Antarctic ice sheets, this one seems to be more vulnerable, so it is probably going to have huge perturbations at the lower end of the warming whereas this seems to be a little bit more robust. As we said, Antarctica is a complicated place because the ocean warming can have different effects of increasing the snowfall while also melting off the ice shelves and moving the grounding line and so on for the glaciers on the mountains. Coral reefs always come up. We have to watch out for our own system. There is some evidence that in the ice ages the monsoon had weakened. So if global warming also weakens the monsoon, then we are in a kind of a trouble, because both extremes are bad for us. Only when in the deglacial, if good monsoon happens, but with this kind of warming, even a good monsoon means a lot of extreme events, then that can be an issue. So we will come to this more complicated figure in the next session, but these are basically examples of observed impacts to ecosystems, coastal sectors, and human health. So we will try to see how any of these systems are responding already in the observed data that we have. So we have to always keep in mind, here are the potential weak points, and here is what they have already been doing because of our emissions since the Industrial Revolution. That gives you a sense of where we are headed. Each system, coastal ecosystem, corals, Arctic ice, jet stream, Greenland ice, El Nino, Samoa land circulation, Antarctic ice, and so on. So constantly keep in mind, it's like looking at the rear view mirror while you are driving, so that you always know what was behind and what it means in the future. Okay, so we'll continue when we come back. See you next time.